So for today, let me start with some context about myself. My name is Siddharth, or Sid, as some people call me, and my domain is autonomous driving or machine learning in the context of autonomous driving. And I thought that this is a great opportunity for me to share some insights on some of the challenges which autonomous driving faces. And I thought maybe why not go into some details into some like go deep into like one particular challenge just to show how it affects the field of autonomous driving. And yeah, let me get started. All right, let me start with some context. Just oh, 1 second. All right, so uh, yeah, so for autonomous driving, we can divide. Um, yeah, this slide kind of illustrates the basic loop of how autonomous driving works. Basically, it's divided into the perception, prediction, and planning loop. The perception system uses the sensors on the self-driving car, like cameras, lidar, and radar, to understand the environment of a self-driving car. Then it's followed by the prediction step, where the prediction algorithm forecasts the movement of other road users based on the observations of the perception stack. And in the final step, we have the planning stage, where the planning module determines the optimal driving path, considering the safety and efficiency of the different agents which were predicted in the previous step. Now, based on this flow, we can see that autonomous vehicles must simultaneously do multiple tasks with a very high accuracy. Like, firstly, they should detect and classify all objects in the scene. Secondly, they should predict what the future movements could be for all other vehicles and pedestrians. And lastly, they should be able to plan a safe trajectory through multiple intersections and like construction zones and like difficult situations. And each component builds on the previous component. So, for example, a poor perception leads to inaccurate predictions, which would then in turn lead to unsafe planning and so on. And recent advances in AI and machine learning have significantly improved how all these aspects of autonomous driving work. But for this talk today, we'll just look at some of the challenges faced by autonomous vehicles in the prediction task, particularly where it's an inherently uncertain system and how we deal with this problem. So basically, this is would translate not just to self-driving cars and autonomous vehicle, but this way of handling uncertainty would translate to multiple domains. But this is just an example in the case of autonomous driving, which can highlight this technical way to handle how we approach uncertain situations. All right, moving forward, I'd like to start with an example. Um, so over here, this is a typical urban driving scene for self-driving cars. It's a simple driving situation. We have a two-lane road which approaches an intersection with the standard infrastructure of an intersection. We have the lane markings, stop signs, and crosswalks, which are kind of clearly visible here. And I will just refer to self-driving car as the autonomous vehicle as AV in short. So we have the AV in purple, which is trying to navigate with regular traffic, which in this case would be two cars, which are like the forward car shown in green and the rear car shown in blue. So I will just mention them as the forward and rear car in case the colors are not clear here. And we also have some pedestrians who are waiting at a marked crosswalk, and they could either cross or wait. So, like, this is a typical situation. which shows the basic elements which the AV must handle. So we have vehicle traffic, we have pedestrian traffic, and then we also have the road infrastructure. Now, um, let's take let's take a deeper look at this from the AV's point of view. So our AV wants to make a right, let's say in this situation, our AV wants to make a right turn to reach its destination. And the right turn is like maybe the shortest path to go there. Now, in this situation, if the AV wants to turn right, it needs to lane change into the right lane and then make the right turn. So, a lane change to the right lane would be the most efficient way to do it, as opposed to, let's say, going straight and then rerouting and taking a longer path. And before lane changing, the AV over here must successfully track the behavior of multiple actors in the scene. It needs to figure out what the blue car or the rear car is doing. It needs to figure out what the green car or the car in front of it is doing. And also, it needs to figure out what the pedestrians at the crosswalk might do. And this situation is inherently uncertain because each actor over here could take different actions. For examples, cars might be slowing down, or speeding up. Pedestrians might start crossing at any time, or they might suddenly stop. And the AV must predict all these possibilities while trying to plan its next move. This really shows how complex real world decisions are for autonomous vehicles. So, to, to sum it up, as I mentioned, we have the rear vehicle, which may accelerate or brake, the front vehicle, which could change speed or trajectory. We have pedestrians, which might cross or wait at an intersection, and the AV must evaluate if it can lane change safely based on all these actors. All right. Now let's switch gears a little and then try to see how we can try to predict the behavior of, let's say, one agent in the scene. So for this example, let's take the example of the forward car, or the car which is shown in green. So it sees a stop sign, and it's approaching a stop sign, and there are two pedestrians who are waiting at a crosswalk. So this particular car, which is another actor in the scene, must consider multiple options here. It could either continue at its current speed, which in this case would be illegal because it's a stop sign. They should ideally wait at the stop sign. They could slow down at the intersection. They could completely stop before the stop sign for the pedestrians, or they could do something completely random, like take a left turn, for example. And it also needs to consider other actors in the scene. So, for instance, behind it, the autonomous vehicle could stay in its lane, or it could try to attempt a lane change. Even the rear car would affect the decision of this vehicle. Um, the rear car could maintain its speed or change its speed and positions, and each actor's decisions will affect the others. So it's an interactive system over here where the action of one person depends on the action of other persons. And all AI actors continuously update their plans based on other behaviors. All right. So, yeah, summing this up, we have a target track where we want to predict what this vehicle will do. In the scene, we also have an AV which might uh, lane change or go straight. We have the rear vehicle which might accelerate or brake, and then we have the pedestrians who might yield or try to cross. Again, like all these actions by different actors are for the green car or the front vehicle, and we have them marked in different arrows because we want to see all the different possible futures which can happen over here. Um, all right, so let's explore why we need multiple predictions for a given actor. This is required to safely capture the risk of, let's say, uh, colliding with another actor or another agent in the scene. And again, going back to our forward vehicle, also another like sort of terminology which we use for having multiple predictions over here. We call them multimodal predictions because we kind of think as multiple probabilities. So yeah, just mentioning that out there. All right. So coming back to our example, if we think about the green car which is approaching the intersection, even if we had perfect knowledge of the world and how things reacted, let's say a human driver is someone who has perfect knowledge compared to self-driving cars or the AI which is used in self-driving cars. So even if we had perfect knowledge in this situation, we would still face inherent randomness. So even a human driver in this case wouldn't be able to tell with certainty what this car would do in this situation. So if there's a cautious driver in this car, they might brake early or they might brake late. If there's a driver who's not paying attention, they might not even look at the stop sign and continue going straight. And all of these are likely choices. Um, but this is an example of the inherent uncertainty which is faced by self-driving cars, and this is something which even human drivers cannot predict. And this is something which, in the context of uncertainty, we refer to as aleatoric uncertainty, or basically the natural randomness in the world, where no matter how much data we throw at a machine learning model or how good the sensors of a car become, there isn't a way for us, or like we cannot predict exact stopping points or know precise timings of decisions or even determine exact trajectories. However, from for the context of AI used for autonomous driving, like let's say prediction machine learning models, we also face another type of uncertainty. And this is referred to as epistemic uncertainty, or basically this refers to the gap in how we train a machine learning model. So one of the common pitfalls is um, that we train our models on one set of data, and then when we deploy our machine learning model, it sees something completely different out there on the road. These are called out of distribution examples. So maybe we have never seen this intersection layout before, or the lack of data about pedestrian behavior at this time of the day could affect the model, or the system might be unfamiliar with this vehicle model, or so on. So the second kind of uncertainty over here represents the gaps in our knowledge um, and this is something where the machine learning model can improve if we give it more data or if we improve the model. So back to our scenario, the green car is approaching the stop sign, and over here, let's say it can take three actions, and this is kind of an output which we want our machine learning model to give, which is like multiple outputs at the situation with varying probabilities, so that it's easier to capture both the inherently random variations in the behavior and account for the uncertainty from the gaps in the knowledge of the AI model. So to sum it up, we're not just predicting one path, but modeling the range of possibilities while accounting for what we don't know. Um, yeah, next slide. So, building on the understanding of multiple uncertainties and diving deep, we want to dive deeper into another type of uncertainty which is faced here. And this is, again, very common to other time series problems, not just the prediction problem in self driving cars, but this is just an example. So let's say even after we predict multiple possible modes, as we call it, or multiple possible paths for our agent behavior, like stopping early or turning right, there's another layer of uncertainty which we need to consider, which is the precise execution of these intended behaviors. So looking at our visualization, the top shows the nominal trajectory or what we expect to do, but the bottom reveals the reality or a growing region of uncertainty of where the car might go. So, just to clarify the figure at the bottom, it is where this car would be in the like where the center of the car would be as we try to predict its motion over varying times. And because uncertainties accumulate over time, as as the time horizon goes forward into the future, we will be more and more uncertain as to where the center of that car would be. So, and this position of uncertainty grows significantly over time, and this could be related to how microscopic changes in, let's say, road conditions, or how much force a driver applies on the braking or on the gas or the acceleration pedal, which can change, which can minutely change and then lead to much bigger changes in the exact position of this particular vehicle. So we can see this kind of growth in confidence intervals, or like how confident we are on an average, from, let's say, if we are predicting something on a 4 second horizon. And this is again back to categorizing the type of uncertainty. Even with perfect knowledge, an AI model can probably not understand, um, like an AI model would still have this uncertainty, because even a human would, if we consider a human to be the perfect driver, would have this uncertainty of growing regions, when it comes to predicting what an actor in the scene could do. All right. So yeah, just building on some terminology, and some summing up so far. Um, we saw that like an actor could take multiple paths, and that is referred to their uncertainty in intent, or like what their intention is. It could be either something where, which is something which is because the AI model doesn't have enough data, or it could be something where we have inherent uncertainties, which even with perfect AI models, it's really hard to get rid of, because those like the environment is just like the environment is a stochastic process, and those uncertainties will exist even for perfect situations. All right, so now I want to go deep into an example for modeling this kind of uncertainties. I'll try to keep this a little general. It could be a little dense technically, but I'll try to keep it more general, just so that we can drive the main idea home. And for people who are more interested in this, I can suggest further readings. Just because this kind of modeling doesn't only apply to, as I mentioned, doesn't only apply to self-driving cars, but it's related to a lot of these time series problems, which we see in a lot of these situations out there. But there's a lot of research done on self-driving cars, so I think this can translate well to other situations as well. So yeah, I want to go through research, and I'm citing this paper over here, which is called the multipath paper. And I'm trying to like going, they have a very good example of handling this. And it's one of the first basic papers which uh, establishes the foundational algorithms. So yeah, that's why I chose this. And yeah, let's take a look at how we can model these uncertainties in practice. Um, yeah, before diving too deep into technical details, a quick note is that I'll be discussing published methods from academic literature, so that it's easy to follow along these concepts. And I think these papers provide a good foundation for understanding uncertainty modeling in autonomous driving. All right, so um, with that, taking a look at this sort of model over here, this is an architecture which provides like an elegant approach to handle both the intent and the control uncertainty. So what we see in this diagram are high level components where we have um, an ML model or an AI model which takes uh, these high level components, such as input features capturing the full context of the scene, an encoder that processes all of this information and outputs that explicitly model both types of uncertainty, which we saw in the previous situation. And over the next few slides, we'll break down each component and see how they work together to create a robust prediction system. And I want to focus on the uncertainty modeling, so I'll just focus mostly on that part. All right. So, um, yeah, if we go back to our previous approach, the way it's modeled is every actor would in this example, the core mechanism uses a fixed set of predefined anchors, or in if some people are familiar with how ML models work for object detection, this would be familiar to them. But essentially, to try and predict what an agent would do, we come up with basic predictions, which are templates, which we store from beforehand, and then try our we try to make our ML model try to predict which is the most likely template from our chosen set of templates. So in this example, let's say if we have 16 possible templates, which a self-driving car can take. The goal of the AI model would be to first figure out, for a given traffic situation, what is the best template which the AI model would use over here. And once we predict what template is going to be used, the second task becomes on predicting how we generate the final trajectory. So this is computed by trying to predict the offset from this given template, and by trying to predict the uncertainty associated at each time step. Um, yeah. So looking at this diagram, the bottom line, let's say, shows our selected trajectory, which was predicted. The top line, or the red line, shows the final predicted trajectory after applying all of these offsets. And show the distances show the learned offsets for each time step. And the pink circles over here show the predicted uncertainty, which is growing over time. And this captures both the types of uncertainty which we discussed above. And this is an example from the paper in a real life situation. So yeah, quickly trying to go a little bit mathematical over here for um, without trying to okay, I'll try to keep it a little high level, but essentially this is a way in which we can sum it up as a loss function for the machine learning model to train it. And again, this can apply to multiple time series examples. So if we can model these noise, like the growing uncertainty over position, as a Gaussian distribution or a normal distribution, which is the most likely situation, and have a similar um, a similar distribution for the templates which we used, we can write out our loss function. And I don't want to go too much into the technical details for this presentation, but essentially this helps us in this kind of representation helps us in modeling our loss for the case of autonomous driving. And if someone's interested, I would, yeah, more than happy if you reach out to me. I'll try to go into details, but here I want to keep it more accessible. So I'll stay a little bit on the higher level. Yeah, that's mostly it. And once we express things as a loss function, essentially our loss function then just breaks down into a lot, like how good did we do the template prediction, and then how good did we predict the offset from that given template. And this kind of helps, just to show it in code, it boils down to a very nice and elegant form, where we can easily compute this kind of representation, and then this kind of helps us to go back into our original representation, where we can think that we can see how multiple ways of uncertainties are represented. So yeah, I guess I want to, in the interest of time, I think I'll probably just stop here. But I know that there's a lot of maybe follow up questions or a lot of directions of research over here which this can go into. So I would be very happy if like someone wants to connect or like go into some details about these technical things. Again, as I mentioned, that I just gave an example for autonomous driving, but this applies to uh, things other than autonomous driving as well. In general, it applies to a lot of different time series data. So yes, that's all from my side. Yeah, if there's any questions, I'll be more than happy to take those.